Good morning, I am Renu Sharma, Assistant Professor, EC Department. Today I am going to start with the next part of this subject, that is wireless and mobile communication. Today we will discuss channel modeling. So these are the contents of today's lecture. Like first one is the introduction of the topic, that is channel modeling, then propagation mechanism, that how we are going to model a particular channel so that there are different phenomena that will going to change the characteristics of the channel because it is a wireless communication channel. Then channel effects are there. We are going to discuss what are the atmospheric effects, what are the conditions that will going to change the characteristics of a particular channel that we are going to will be designed. Then multipath scenario will be there because there is no direct line of sight exists between the transmitter and receiver. There is a multipath scenario exist, and then we'll discuss the free space propagation mechanism, that is the numerical part of this particular topic. So this is the introduction of channel modeling. A wireless channel is nothing, it is a dielectric unguided medium. Why we are calling it unguided? Unguided means there is no direct line of direct communication link has been set up between the transmitter and receiver. It is a non-wired kind of medium, that is unguided medium. There are two types of medium that exist, that is guided and unguided. So in case of this wireless mobile communication, we are dealing with the unguided medium. So it is an dielectric unguided medium that can be analyzed in the one of the different from the following ways. Like first one is by using the fundamentals of the electromagnetic wave theory, such as phase velocity, phase propagation constant, amplitude, frequency and phase. So these are the different parameters that we are going to consider for designing a particular channel unguided medium, channel which is an unguided medium. Like we can consider phase velocity, then phase propagation constant, we'll consider amplitude, phase and frequency of the particular signal that is being transmitted, that is an electromagnetic signal that will be transmitted or radiated in the space. Second is by using the ray theory, refractive index dependence, reflection, refraction, diffraction. So these are some of the parameters that we have to keep in mind while designing the channel, that whatever signal we are transmitting from the transmitter or radiating, it will going to intercept on various devices, various things like trees will be there because there is no direct line of sight exist between the transmitter and receivers. So obviously it will going to intercept on tree, it will going to intercept on it may be a car, moving car will be there, so it will induce the Doppler effect in that condition. So there are various things that you have to keep in mind while designing the channel. Third type is by using the fundamentals of digital signal processing, such as channel transfer function, spectrum channel, impulse response and the convolution with the transmitting signal. So in this case, this is the third one which we are going to discuss for designing a particular channel. Let's say this is a transmitter, this is a receiver, and in between this there is a channel. It can be wired or wireless, but we are dealing with the unguided media, that is wireless channel. So this will going to produce a signal which is denoted by, let's say it is denoted by ST. Then it will going to travel over the channel, and over the channel it will be affected with the noise. Let's say it is denoted by this NT, and at the output we are getting a signal means which is being received or which has to be transmitted after the channel, it will be denoted by YT. So while designing this particular very simple model, we are not using any other intermediate node, we are not using any other device, like there may be possible router will be there, so it has their own parameters. We are dealing with a very simple diagram which has a input signal ST, it is in time domain, then it will be modulated with this noise signal that is denoted by NT, and then YT signal will be generated. So most of the time in communication system, when we are talking about the mathematical analysis of any channel or any sort of application will be there, so we are dealing with the noise that is AWGN noise, that is additive wide Gaussian noise. So first we have to convert this signal into the frequency domain, and we are talking about the convolution. So in time domain, if we are doing the convolution, then in frequency domain it will be multiplied, and when we are dealing with the multiplication in time domain, then reverse will be there in case of frequency domain. So what will be the equation? At this will be YT upon ST will be is equals to NT. So this is the equation, means this multiplied by this one will get this signal. So this is in terms of time domain, and when we are dealing with the frequency domain, so we have to just perform its Fourier transform. So that is the basic idea behind this channel modeling. These are the propagation mechanism, like various types of terms that are involved when we are dealing with this mobile communication. Like first one is the line of sight. The line of sight propagation is the wave propagation in which the EM wave, EM ray follow a straight line from the transmitter to the receiver, which means it is basically dealing with when there is no intermediate node exist between the transmitter and receiver, and we can directly transmit the signal from the transmitter to the receiver, and that will basically occur in open areas mostly, because in case of suburban and urban areas there will be buildings will be there, and there are lot of intermediate nodes or intermediate propagation effects will going to affect the signal. So that's why line of sight exists when there is no population exists, very less population is exist. So second one is non line of sight, that is an LOS is based on and is resultant of the following mechanism. Now when there is no direct line of sight exist between, means an LOS, then what are the terms that will going to affect the quality of the signal? Now, there are basically four things are there, that is reflection, diffraction, scattering and refraction. Now in case of this reflection, this occurs when the propagation wave impinges on an object that is larger than its wavelength, which means whatever signal we are transmitting, it has their own amplitude, phase and frequency, and when that particular frequency is higher, having that higher value as compared to its wavelength, then it is known as reflection. Example of such objects are the surface of earth, building and wall, which means the size of the object is greater than the wavelength of the signal which is been radiating. Second one is the diffraction. Now this occurs when the radio path between the transmitter and the receiver is obstructed by a surface with sharp irregular edges, which means that whenever the object is there which is having the sharp edge, and at that edge the signal will going to intercept, then there will be change of the signal characteristics will be will take place. So that comes under diffraction. Third one is the scattering. This occurs when the propagating wave is obstructed by objects that are smaller than its wavelength. So this occurs when the size of the object is smaller, whereas in case of diffraction is when the size of the object is larger than the particular obstacle. Now refraction is due to the variation in the refractive index of the atmospheric layer, the EM wave will going to bend. So in the cases other than the satellite communication, means when there is a change of particular refractive index will be there from N1 to N2 medium, when there is a change of medium will there, then refraction will take place. So this is the diagram figure 1, which is showing that what are the different 4 factors. Like first one is the diffractive signal, which when the signal from the elevated base station will be there, and it will going to impinge on this particular sharp edge object. Object is means it is a building obstacle. Second obstacle is a car which is moving in nature. So from here the scattering will take place. This is a mobile receiver. This is an example of the reflected signal. This is an example of direct line of sight which exists between the transmitter and receiver. So this diagram is showing that how the four different parameters, different terms that will going to affect the channel quality, signal quality. Now these are the channel effects. First one is the attenuation, second one is fading, third one is shadowing. Now in case of this attenuation, it is the drop in the signal power when it is being transmitted from one point to another, and then it is caused by the transmission path length, obstructions in the signal path, and multipath effects, which means when there is an attenuation which exists between the transmitter and receiver, so the signal will going to it will be changed from transmitted from one point to another, and it is caused by transmission path length, obstructions in the signal path. So all these channel effects will basically will occur due to the different obstructions that exist between the transmitter and receiver. Second one is the fading. As the signal travel from one point to another point, then there will be large number of obstructions will be there, then it will going to change the energy of the signal will get reduced due to the fading. So that is known as fading. So fading is as there are obstacles and reflectors are there in the wireless propagation channel. The transmitter signal arrives at the receiver from various directions over multiple paths. Let's say this is first path, this is second path, this is third path. So at the receiver it will be received from various paths, and this is only one transmitter. So you can see that single signal will be received from three different paths. So that will going to change the characteristics of the signal. So that is the fading of the signal will be there. The third one is the shadowing. This occurs whenever there is an obstruction between the transmitter and receiver is there, and it can be observed in long distance as well as short distance communication. It is generally caused by building and hill. So these are the another type of obstructions will be there due to the building and hill. So that is shadowing. Now next is multipath scenario. Now you can see in this particular diagram that this is the mobile receiver and this is the transmitter. It wants to transmit the signal at this point only, and you can see that what are the different paths that particular single signal will going to follow. This is ray 1, this is ray 2, this is ray 3. Means these are the three different signals which will be received at the mobile receiver. This is the reflected ray and this is the direct ray which will be transmitted from the transmitter to the receiver. So this is the multipath scenario case. Now next we will head towards a derivation, that is a free space propagation scenario. In this particular free space propagation model, this formula which we are going to derive is the received power at the receiver. So whatever signal which we are transmitting from transmitter to receiver, it will be received, and what power it has that we are going to calculate. So there are certain 4 or 5 parameters that will be used to calculate that particular received power. So Friis free space model is valid only for the values of D that are in the far field of the transmitting antenna and less than the radio horizon. So these are the two figures that are used to study this particular free space propagation model. Like you can see, we are going to consider a isotropic radiator. Isotropic radiator or a isotropic antenna is one which is mostly used as a reference for the mathematical analysis, because its radiation pattern is spherical in nature. It will going to radiate the energy equally in every direction. So this is the radiator. Transmit the antenna acts as an isotropic source of the radiated power. This is the received antenna aperture. Now this is the spherical wavefronts are available and the flux density varies inversely with the D. So this is how we are going to consider the particular isotropic radiator. So the far field is called as a Fraunhofer region from the name of its inventor. So for carrier wavelength, we are considering this diagram also, which is having this particular antenna which will going to radiate. This is near field and this is far field. So we have to consider, we have to calculate a distance also, that is known as a Fraunhofer distance. Now from here onwards the derivation is there. Now we have to consider an isotropic source of the transmitted power, which may be half wave dipole antenna. The flux density at a distance can be calculated as F is equals to Pt upon 4 pi d square watt per meter square. So what is this one? This is the transmitted power, which is written in terms of watt. Then d square is the distance between the transmitter and the receiver. So this is the distance between the transmitter and the receiver, and its unit is meter square. Now considering the gain of the transmitting antenna, if we are considering the gain, because we are till this point we are considering the isotropic source. Now isotropic source is going to radiate equally in every direction, so gain of that particular antenna is 1. But what if we are considering the directive antenna? In that case the gain plays a very important role. So we get an effective isotropic radiated power, that is EIRP, which is equals to PT into GT. Now F will be is equals to PT GT divided by 4 pi d square watt per meter square. So the power PR received by the receiver antenna with an area that is given by this formula, that is AR is equals to flux power density multiplied by area of the receiver antenna that receives the particular flux density. So that is the power that is the area of that particular antenna. Now this will be is equals to F multiplied by mu into AR watt. Now where eta AR is nothing, it is the effective area of the receiving antenna, and eta is the antenna aperture efficiency, so which we can calculate, that is denoted by eta into AR. Now substituting the value of F, PR will be equals to PT GT AE. Now PT is the transmitted power, GT is the gain of the transmitted antenna, AE is the effective aperture area, and D is the distance between the transmitter and receiver. So these are the till this point 4 parameters are required. Now the receiving antenna gain, the gain of the receiving antenna can also be written as GR is equals to 4 pi AE upon lambda square. So that can be written as 4 pi AE upon lambda square. So PR will be equals to lambda square upon 4 pi D whole square multiplied by GT, PT and GR. So that is the gain of the transmitter antenna, gain of the receiver antenna, and this is the power of the transmitter antenna. So this is the power of received power. So after after substituting these values, we are getting this particular formula, that is the received power, and this is also known as the Friis formula, and this model is known as free space propagation model. This is very important formula for studying the free space propagation model. Then we can calculate the path loss also. So PLDB, that is denoted in terms of decibel only. So 10 log PT upon PR, that is the transmitted power upon received power, which is equals to 10 log 4 pi D whole square divided by pi square, that is the unity gain condition, and that can also be written as minus 10 log lambda square upon 4 pi D whole square. So if the wavelength is constant and the loss simply depends upon the distance D between the isotropic transmitter and the receiver, so that is the case. So the overall formula after constituting this path loss model, path loss also, so PR will be equals to PT GT GR lambda square divided by L multiplied by 4 pi D whole square. So where L is the system loss factor, which is not related to the propagation. So there are two types of losses there, system loss factor and the loss that is related to the path loss. So it may be greater than or equal to 1. So L can be considered when there are no losses. So that has to be kept in mind. So this is the received power. Next, we are going to calculate the different noise parameters. Like first one is the noise factor. For components such as resistor, it is the ratio of the noise produced by the resistor to simple thermal noise of an ideal resistor. So, noise factor or the noise factor is calculated as signal to noise ratio at the input divided by signal to noise ratio at the output. So, when we are dealing with the analog communication, we are not dealing with the digital communication. In that, the parameter that is going to specify the particular characteristics of the signal, that is denoted by signal to noise ratio, which has to be calculated at the input divided by at the output of the particular device. So, that is the noise factor. After keeping all other factors in mind, like the gain of the antenna, then this is the Boltzmann constant, this is temperature, room temperature. Now this is the bandwidth, this is the change in noise will be there. So that is also the formula of F noise. Then next one is the noise figure, that it is the figure of merit. Noise figure is the noise factor converted to decibel notation. So when we are converting this F noise into decibel, 10 log F noise, then that is known as the noise figure. Then there is another parameter is there, that is figure of merit. Now figure of merit and noise figure are inversely proportional to each other. Third one is noise temperature. So it is the measure for specifying the noise in terms of an equivalent temperature. So equivalent temperature will be, its formula is, this is the universal formula, that is T is equals to F noise minus 1 multiplied by T naught, and TE will be equals to NT log. If you want to calculate in terms of, because most of the time this noise figure is given in decibel only, so you have to just anti-log, take the anti-log of that particular value and then put in this formula, and you can calculate the TE very well. So that is the noise temperature formula, and these are the references that you can consider for this particular channel modeling topic and various noise parameters. Thank you.